Welcome to the Distinguished Lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers, but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The Distinguished Lecture series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome.
Okay, hello everyone. It is my great pleasure and honor to introduce Tadashi Tokieda as our distinguished speaker today. Tadashi is my colleague. He's a professor of mathematics at Stanford. He grew up as a painter in Japan, became a classical philologist, which is a study of languages in historical texts, and not to be confused with a philosopher, in France before switching to mathematics and physics. He got his PhD from Princeton and worked in Cambridge for many years before moving to Stanford. Tadashi is famous worldwide for his varied and remarkable interests in mathematics and physics and his amazing lectures, some of which you will find on YouTube and other places. He's also active in outreach in the developing world, especially in the African Institute of Mathematical Sciences. Without further ado, I'll hand it over to Tadashi to begin the lecture. Thank you.
We humans tend to be better at physics than at mathematics. After all, when an apple falls from a tree, there are more of us who can catch it. Our physical intuition, you see, tells us how an apple moves than those of us who can compute its trajectory from a differential equation. Therefore, it is natural to apply physics to mathematics, although historically, as you know, the applications have been in the other direction. The purpose of asking for the pleasure of your company in the next 45 minutes or so is to allow you to sample a number of entertaining and sometimes profound instances of these applications of physics to mathematics. As a first example, I shall derive Pythagoras, the most iconic of these geometry theorems, from physical considerations. Let's say we have a triangle PQR with a right angle at R, and our business is to, of course, establish the standard identity among PQ, QR, and RP. Using this triangle as a base, we shall construct a box, all enclosed on 5 sides with height h, and attach that box to, where P used to be, to a vertical axis, so as to pivot it and so that the box can freely rotate around that pivot without any friction. Now comes the curious step of this demonstration. I fill this box with gas at pressure P. This gas is going to press against all sides of the box, but the pressure above and below cancel each other, and there's no degree of freedom in that direction anyway. So we shall look at the lateral pressure distributions. This is a bird's eye view, P being now the pivot, and you have gas pressing against all sides of this triangle. The entire distribution of pressure along the side PQ, I say side PQ, but remember that there's a height h, so this is really a wall, a rectangular wall, PQ, can be replaced by a single force, a representative force, which is acting normally and at the centroid of that side, which we shall naturally call F of PQ, and that likewise F of QR and F of RP. It's apparently from the picture that F of PQ tends to rotate the box counterclockwise, anti-clockwise like this, whereas the other two forces conspire to rotate the box clockwise. However, there is no such thing as perpetual motion machine. So you cannot set the box rotating just by filling it with gas. That's not going to happen. Therefore, the torques must balance. That is, the tendency of this force FPQ to rotate it anti-clockwise must cancel the tendency of those two forces to rotate the box clockwise. So torques must balance. I shall fill the torque formula. The torque due to FPQ is easily computed because that's the distance from the pivot P to the line of force, that is half of PQ here. And similarly, for the torque due to FRP, the distance RP half of RP times FRP. So far, you notice we have not used the hypothesis that this was a right angle triangle. It is here for the first and last time that I invoke this hypothesis. I claim that because R is a right angle, the torque due to FQR around P is exactly equal to 1/2 of QR times that FQR, because indeed, if R were a little less acute, the line of force would pass a little more acute, excuse me, the line of force would pass nearer P, and if R were more obtuse, then the line of force would pass farther from P. But because R is exactly at right angle 90 degrees, this line of force passes in such a way that the distance from P to that line of force is exactly half of QR. This is the only place where the right angle hypothesis is used. But now we are almost home. What is a force after all? It is pressure times area. So it's P, that's the pressure, times H times PQ, for example, for FPQ. That's the area of that side, which is actually perpendicular to the picture, and so on. And similarly for the other ones. And you see when you write it out that the half small p h appears in all terms. So by canceling these, you get PQ squared equals RP squared plus QR squared. Congratulations. If you conducted the same Gedanken experiment, thought experiment on an arbitrary triangle, which is not necessarily right angle, then you would be led to what is called the cosine law. That was an inequality. That was, excuse me, an equality, Pythagoras. Let's see if we can handle inequalities as well. The most famous and perhaps the versatile inequalities of all time is Cauchy-Schwarz inequality. In the former Soviet bloc, Cauchy-Schwarz-Bunyakovsky inequality. Imagine a number of slats of wood, if you like, or plates that are horizontal and they're in mutual contact with, neighboring contacts with one another, and they're sliding against each other. All right. The first slat has mass m1 and moving at speed v1. They are all moving in the horizontal direction as shown. And the second slat m2 is moving with v2, third slat m3, v3, different velocities, different masses, and so on. This is the initial condition. We prepare it and release. We wait for a while and we know what happens physically. After a while, eventually, asymptotically more precisely, they end up moving at the same speed because of the mutual frictions. They equalize the speeds. That's the before and that's the after. We shall denote by triangular bracket of V, the average of V at which all the slats may end up moving at the constant speed. This average V is actually easy to compute because you see all the forces are internal. There's no input from the outside or output to the outside. So the momentum is conserved in the meantime, which means that the sum of MVs is equal to, well, at the end, all the slats are moving as if they form one single mass. So the sum of the masses times this representative velocity bracket of V. So bracket of V can be computed by this formula, sum of mv divided by sum of m. While momentum is conserved, the energy is dissipated because of the mutual friction. Something is lost to heat. Before and after, the energy is easy to write down. Also, before it's sum of half mv squared, yeah, for various indices. And then afterwards, it's half times all the masses are bunched together now, the sum of masses, times this bracket velocity squared. Yeah. However, we know what this bracket velocity is. We can just plug in this formula into this energy. And you see that the dissipation means that there is an inequality. Before is greater than or equal to after. By clearing the denominator, what you get is sum of m's times sum of mv squared is greater than or equal to the square of the sum of mv. This looks almost like Cauchy-Schwarz, but not quite in the familiar form. And in order to get to the familiar form, we should make a change of variables. Let's replace each m by m squared, and each v by v over m for that index. Yeah? And then this inequality gets transformed to the sum of m squared times sum of v squared, because you see m is replaced by m squared, but v now has v squared over m squareds cancel, and so on. On the other hand, the right side of this inequality is invariant under this transformation, which has some significance. And so you have this familiar form of Cauchy-Schwarz. Good. You might complain, and you would be right, that, well, in Cauchy-Schwarz, all those m's and v's should be arbitrary real numbers, so they don't have to be restricted positive. But of course, in the physical constellation, m's have to be physically positive. But that's fine, because you see, in the result, the reversing the sign of m doesn't affect the left-hand side, but the right-hand side is affected, you see, but the m does appear always with v, m in the form of mv. So reversing the sign of a certain m is the same thing as reversing the sign of v. In other words, you can make the slot move to the left rather than to the right. And so that takes care of the sign issue. But when we talk about an inequality, it's also interesting to discuss what the sharp case is. When does the equality case, the critical case of an inequality, take place? Well, go back to physics. Equality means that there was no dissipation of energy. And what's the only scenario that leads to no dissipation of energy? Obviously, when all the slots are moving with the same speed to begin with, right? If there's any gradient of velocity, any neighboring differential in velocity, of course there will be friction, and some energy will be lost. But that means v1 equals v2 equals v3, and so on and so on. That was in the old variables. In the new variables, you remember this change of variables? It says v1 over m2 equals v2 over m2, and so on. v1 over m1, excuse me, equals v2 over m2, and so on and so on. And this means that all the components of v as a vector and all the components of m as a vector are proportional. That these vectors are proportional, and that's indeed a sharp case of Cauchy-Schwarz. Equally famous and differently useful is the inequality AMGM inequality. That's the abbreviation for arithmetic mean geometric mean inequality. To remind you what it is, if you have three positive reals A, B, C, let's say, the usual average, it's called the arithmetic mean that we think about, is A plus B plus C over 3. That's fine. But there's another equally useful average, which is the geometric average. That's the multiplicative counterpart to this arithmetic thing and additive thing, which is A times B times C, and everything taken to the cubic root. And the AMGM inequality says that the former is greater than or equal to the latter. Let's derive that from physical considerations as well. I consider a number of lumps of the same material and with masses m1, m2, m3 in mutual contact with one another. Here I drew a cartoon for 3 masses, but that's in general, you have n of them and all in contact with one another. Having the same specific heat, C. What is the specific heat? It is the amount of heat that you have to put in to raise the temperature of that material by 1 Kelvin for each kilogram. Okay, if you like, it's the thermal inertia. So how resistant or how reluctant the material is per unit mass, per unit degree of temperature to the change of heat. Okay, so that's what it is. So something with a great specific heat is very hard to heat, but once heated, it's very hard to cool. And something with a small specific heat is easily cooled and heated and so on. All right. And that's why when you touch, for example, metallic surface, it's clammy to touch, you feel it's cold, although it's actually at the same temperature as the ambient temperature, whereas if you touch wood, it feels warm and so on, because the difference of specific heat. Okay, let's go back to MGM. We shall introduce a notation. P sub I is m sub I, small m sub I, divided by the total m, that is the sum of all the m's. In other words, the proportion that each mass occupies in the total sort of material ensemble here. So PIs. PIs are therefore, if you like, weights and equal weights or probabilities, and they each belong to P and the interval 0, 1, and they add up to 1. Okay. Now, say that the initial temperatures of those lumps are T1, T2, and so on. So the bodies are then placed in thermal contact, and we sit back and watch. Well, what does physics tell us? We know, because we have lived in this physical universe for a long time, that they eventually settle, after exchanging heat, to a common temperature. And that common temperature is readily computed. Again, the same notations, triangular bracket of T is equal to the weighted sum of all those initial temperatures. That is the sum of Pi, Ti, all right? Let's say in the course of this process that for a short time interval, we are looking, the ith body changes its temperature by a small increment dTi, okay? Then the heat during this short interval that it received is equal to the specific heat times the mass times the temperature change, that is C times MPI, afterward that is what the small mi is, times the temperature change dTi. So now comes the real protagonist of this argument. The entropy of the ith body changes by, the entropy is for historical reason always denoted by S, dSi is the heat it received, that's the numerator, divided by the absolute temperature at which it received the heat. If you like, this is the thermodynamic definition of entropy. There are other definitions of entropy, they're all equivalent. For example, statistical physical one counts the number of states that correspond to some macro state, and then take the log and multiply by the prefactor Boltzmann constant and so on. There's also an information theoretic entropy, which we shall come to later on. Anyway, just don't worry about this. This is the definition of entropy, and you recognize that dt over t is, of course, the logarithmic derivative. So the final answer is that the dSi, the change in entropy for the ith body for this small temperature change, is equal to C MPI times d of log Ti. We copied that formula up here. And now let's run the process from start to finish. That is, from the initial state, and then we just wait for infinitely long, but in practice, long enough, so that the common temperature is achieved. Well, the entropy, that means to integrate this formula. Entropy at the finish for the ith body minus its value at the start, that's the integral of this, is equal to Cm is a common factor, and Pi times, well, it's the final value of log T, which is the log of that triangular bracket, the common temperature, minus Pi, the initial value of log T, which is log Ti. Here I'm committing the sort of prime or les notation by denoting the two concepts, the initial temperature and the variable, by the same letter Ti. But please forgive me, this is the last time that you see this confusion. Okay. That was for the ith body. Now sum over all the i's, that is for the whole system, you have the sum of the entropy change equals Cm, and as pi's add up to 1, you have this 1 here, and instead of adding this, first put pi inside log so that it comes on the shoulder of Ti, and then you sum the logs. The sum of log is, of course, log of the product, so you get log of the product of Ti to Pi. So far, it has just been descriptive, but now I invoke the second law of thermodynamics, which says that the total entropy change for a system, for a spontaneous process, must be positive. That means that in the right-hand side, the inside of a log must be in the correct order. That is this arithmetic mean, which is the sum of pi's, pi, ti's, pi, ti plus p2, t2, and so on, is greater than or equal to the geometric mean, which is ti to pi times t to the pi, p2, and so on, so on. So you get this arithmetic mean, geometric mean inequality in a slightly more generalized form, allowing for unequal weights, unequal probabilities, if you like. What about the sharp case? Well, the sharp case means that there was no heat exchange, and surely that happens only, we know this from experience, when the initial temperatures were equal. That is, when TIs are all equal, and that is indeed the sharp case of AMG inequality. So, mazal tov. Speaking of entropy, we can use this kind of argument, physics to mathematics, to discrete and indeed number theoretical problems as well. We shall, as an amusement, derive the infinitude of primes, prove that there exist infinitely many primes. In order to do this, we must remember something from information theory, but the only thing I ask you to remember and indeed accept is the following economical fact. That is, if you want to code a number of the size n, a natural number n, it costs you, it's not free, it costs you some information cost, and that cost is log of n bits. Yeah? It's traditional to take log base 2 because of various circumstances, but any log is, of course, proportional to each other. So it doesn't matter which base you take. Yeah, and this should be obvious because you see, never mind coding, it actually takes those bits, this many bits, to write down the number n to record it to begin with in base 2. Yeah, so even before you start coding, this is the lower bound, and indeed you cannot do any better. So it takes log n bits to code something, a number n. You should remember this. So it takes, for example, log 10 bits to code 10 and log 100 bits to code 100 and so forth. Okay, let's then imagine coding an arbitrary number n. Before doing so, we shall take a detour and first write down its prime decomposition and prime factorization. So it's going to be written as the product of p to e. So various p's are all primes and various e's are all exponents. Here, all but finitely many of those exponents are 0. So it looks like an infinite product, but that's okay. And it ends up being a finite product. Okay. Coding n then is equivalent exactly to coding all those exponents. If we know those exponents, we know n and vice versa. But now let's ask how much it costs in information theory terms to code each exponent. In order to do so, we should extract just one factor from this product, which then is of course less than the total product. So n is greater than or equal to pi to ei for some specific I. As the smallest prime is 2, this in turn is greater than or equal to 2 to ei. Now we can take log base 2 on both sides, and we get that the ei is bounded above, that's a good bound, by log base 2 of n. Yeah? So this is how large each exponent can be at most. But now we can use the boxed fact. Coding ei then costs, you see, each one is at most log n. So it costs log n to cost. Yeah, each ei costs at most log n bits to code. So far, everything is correct. But now let's start arguing by contradiction. Arguing by contradiction, suppose that only finitely many primes exist in the universe. Let's say a capital K of them. K might be gazillion, but it is finite. But then we will be in trouble because by the line above, n would cost only capital K times log n bits to code because there are only at most k exponents to code. Yeah, so k times that log n is the maximum cost, and that's absurdly cheap because that would be much less than the true cost log n as n grows to infinity, yeah, asymptotically. In other words, if only finite many primes existed in the universe, then we would have an impossibly cheap way to code numbers, and that's not possible. That contradicts the basic laws of physics or the basic law of information theory, which is more or less the same thing. Therefore, the only escape is that the hypothesis was wrong. Infinite many primes must exist. Physical thinking is actually quite amusing and sometimes powerful in the whole range of discrete and algorithmic problems. And as an illustration, let me digress on a little game, which I call multiplicative scoring. Let's play the game of splitting a number additively. So let's take k, all the numbers that shall appear are natural numbers. K is split into I and k minus I. So you see they still add up to k, but I put it in two terms. Okay. When you split it like this, I shall decide that I score a score of I times k minus I, the product of those two terms. Okay, so here's an example. You can start from 6 and then split into 2 and 4, that's fine. And then 2 might split into 1 and 1. There are many different ways of splitting, but this is just an example, yeah? And 4 splits into 1 and 3, 3 splits into 1 and 2, 2 finally splits into 1 and 1. So you split all the way to 1s. By the way, I've always complained about what computer science do. When they draw a tree diagram like this, as they say, they tend to put the root at the top and leaves at the bottom. They seem to think that the tree grows downward, starting from the root at the top. Well, as far as I know, trees tend to have a root at the bottom and grow upwards. So I don't know why the diagram is not drawn with the root at the bottom, but never mind. So this is the diagram. So what are the scores? When you split into 2 and 4, you score 2 times 4, that's 8. And when you split into 1 and 1 and 1 and 3, you add, you score 4 and so on. So the total score for this particular tree, splitting algorithm was 15. So all fine. Now I ask, what splitting algorithm, what particular way of what particular tree of splitting maximizes the total score? So, I did it in one way, but maybe if I did it in another way, I would have changed the score. And then what is the way to maximize the score? Those of us who are over-educated might start wondering, well, maybe AMGM inequality, because we're trying to maximize the product while keeping the sum constant and all that kind of thing. But it is a difficult problem, except if you start thinking physically. Let's imagine that you receive lots and lots of parcels, lots of cardboard boxes, all of the same size, all of the same weight. And I'm going to start stacking those boxes into one single tower. As it is difficult to do, I'm going to ask Professor Chatterjee to help me. So the two of us are trying to lift a tower of I and try to put it on a tower of k minus I to make a tower of height k, okay? I asked, well, it's hard work. How much energy do we need to do this to achieve this potential difference? Well, the potential energy for stacking is, in this case, I times k minus I for this stacking. How so? Well, it becomes a bit complicated if you start thinking, well, I take the top box and put it at the top here, and the bottom box and take it on the top of that, and so on. But think of it this way instead. Imagine this stack of I and lift it vertically up, just translate it by a height k minus I. So in doing so, each of those boxes rises by a height of k minus I. And once you do that, you slide the whole thing sideways and put it on top of the weighting stack. And that horizontal slide does not require any potential energy. And so that means you get I times k minus I, okay? And now you recognize that this is the same as the score. In other words, our stacking exercise is inverse to the game that we mentioned before. Now we can go to town. Let's say that you start with n parcels that are all lying on the ground on level 0, and at the end you want to stack them into a single pile, and the ground level being 0, next level being 1, and all the way to n minus 1. Please be careful. This is the, if you like, the European way of counting the floors, not the American way. So the ground level is 0 because sliding anything sideways does not cost you potential energy. So you have those. And you're asking, well, what is the total energy required in order to do this? Well, that's the sum of 0 plus 1 plus 2 plus all the way to n minus 1, which is n minus 1 times n over 2. And we notice that this is independent of what happened in between, that is, of the splitting algorithm. So because of this physical interpretation, physical, in fact, mirror of this game, we know that, in fact, the question was completely moot. It doesn't matter what you do, unless you do something stupid like going backward and so forth. It's always the same. Do whatever you like. It's always going to be the same score at the end, and that's 15. 15 was actually equal to 6 minus 1 times 6 over 2. Let's now move on to another topic, which goes back to the 19th century, and this actually prepares us for something a little greater. Speaking of the discrete, discrete mathematics is sometimes harder than continuous mathematics, not perhaps theoretically, but in what I call combinatorial junk corrections. There are lots of those terms that in the continuous case disappear because you are taking the limit, but in the discrete case survive and torment us. Pick's formula talks about the area of a lattice polygon. Let's consider the integer lattice on the plane, that is all the points that have integer coordinates. And a lattice polygon, by definition, is a polygon drawn on such a picture so that its vertices are all the lattice points, or lattice points. It doesn't matter if the edges go through some funny places like this. As long as the corners of this polygon are lattice points, then it is a lattice polygon. And you ask, what is the area of a lattice polygon in terms of the lattice information, the discrete information that we have? Well, we are now used to the civilization of pixels. It's natural to count the number of pixels, or if you like, number of interior lattice points, and take that as a first approximation. So this is the number of interior lattice points of the polygon lambda. Well, but let's be a bit more precise. There are also boundary points that we should count. And, a boundary point is half in and half out, sort of. So I'm going to count the number of boundary points and then put the weight 1/2 and add that as a correction. And it turns out, if you subtract 1 at the end, you get the exact formula. Amazing. This -1 is always regarded as mysterious. We shall come back to that. That's the combinatorial junk correction that we don't quite understand at the moment. But anyway, it is the exact formula. So for this particular example, the number of interior points is 1, 2, 3, 4, 5, 5. And then there are 11 boundary points. So half 11 minus 1, that turns out to be 9.5 is the area of this lattice polygon. That's Pick's formula. Before we prove Pick, to derive Pick from physics, a little digression. Pick's formula tells us interesting things that are not often popularly known, and that is the question of which regular n-gons exist in the lattice geometry. There do exist regular four-gons, that is regular squares. For example, you see one, or you can see something that is losange, sort of standing on its tip like this, or you can have a tilted version. Regular four-gons are easy to draw in lattice geometry. It turns out that those are the only regular n-gons. In other words, the regular n-gons do not exist at all in lattice geometry, except when n equals 4. For example, equilateral triangles don't exist in lattice among lattice polygons. Okay. I shall prove this from Pick, and it is a digression. This entire talk is in some sense a digression, but the digression for n equals 3 first. Arguing again by contradiction, if such a thing existed, if n equals 3 regular three-gons existed among lattice polygons, then its area would look like square root of 3 times half an integer. And the reason is, if you have, say, lattice triangle whose base is, let's say, b, well, its height is going to be something like square root of 3 times b over 2, right? So if you take the area, you do get square root of 3 involved, you can't get rid of it. And it's going to be half integer afterwards. But look at Pick's formula. Pick's formula says that for a lattice polygon, the area must always be at worst a half integer. There's no such thing as an irrational square root of 3. That never appears. So this is impossible. Yeah? Such a thing does not exist if Pick's formula were correct. N equal 4, yes, exists, but n equal 5 or above, here's an argument by what is called descent. By contradiction, let's suppose that there do exist lattice, let's say 5-gon, and take the smallest of such lattice 5-gons, because this lattice geometry, you cannot be arbitrarily small. There exists a minimal lattice pentagon. Okay. A lemma. If in a parallelogram, 3 corners of the parallelogram are lattice points, I claim that the 4th corner is also a lattice point. That's easy, right? By parallel translating from one to the other. But that lemma says that in this picture, for example, by looking at those 3 points, that point is a lattice point. And you can keep doing. By looking at those next 3 points, that point is a lattice point. That's a parallelogram, and so on, so on, so on. And presto, you got a smaller pentagon, which contradicts the minimal choice that we had made in the beginning. So this is a case of descent, infinite descent, which happens. And because we are in a situation where infinite descent is not possible, lattice geometry is bounded below, so you cannot have lattice n-gons for n starting from 5. Going back to Pick itself, let us prove this formula, let us derive this formula from a physical consideration. In order to do so, I hope that this lecture will be watched by lots and lots of people, indeed infinitely many people, and I ask infinitely many members of the audience each to stand at the lattice point on the plane. So all the planes, the entire plane is occupied by my esteemed audience, and each person at the lattice point is holding an upside down glass filled with volume 1 of water, okay, and it's now sealed at the moment. And at the whistle of Mahan, everyone is asked to lift the glass and then flood the plane. Well, because each lattice point had 1 volume of water, the plane floats, and when the water settles, it settles to depth 1. Yeah? And the volume of water that ended up above the picture of lambda, our lattice polygon, is equal to, of course, the area of lambda because the depth is 1. Okay. So we ask, where did the water above lambda come from? The key remark here is as follows. You see, there is a symmetry in this fluid flow. When you all flood the plane, the water flow is going to be extremely complicated all over the place. But we can say this, that if you look at the midpoint of any edge of lambda, it doesn't have the lattice point itself, but its endpoints are lattice points, yeah? And because all the lattice points are equivalent, in some sense symmetric, the flow across this edge is symmetric. In other words, if there is some flow in one direction across this edge, there will be a counter flow, exactly the same amount, but in the opposite direction across the same edge, because of the symmetry of the lattice structure. So the net flux across every edge of lambda is 0. That is very useful, because that means that without loss of generality, log, sometimes this abbreviation stands for without lots of generality, we can assume that the boundary of lambda is impermeable. That is, we can assume that no water went in, no water came out. Yeah. So we shall do that from now on without loss of generality thanks to this symmetry argument. Now, where did the volume of water then above lambda come from? We can assume that lambda is now the boundary lambda is just a solid wall, not allowing the passage of water. So that simplifies the question. So for each internal point that is inside lambda, that internal point contributes one volume of water, of course, because it starts and then water doesn't go out, doesn't come in, so it ends up inside lambda. As for a point on the edge of lambda, you see you start floating in all directions, but half of the water goes inside lambda and half of the goes ends up outside lambda. So pi out of 2 pi worth, that is 1/2, ends up inside lambda. What about a point that is on a corner, that is a vertex like this? Let's say that the vertex angle is theta. Well, then theta out of 2 pi of water ends up inside lambda. Yeah. However, we know that for an n-gon, in general, the sum of the internal angles theta is equal to n minus 2 times pi, because you can divide that polygon into n minus 2 triangles. Okay, so dividing through by 2 pi, you get the sum of theta over 2 pi is equal to, now look at this, you divide by 2 pi is half n minus 1. Okay, and look at those colors. Internal lambda, that's green, that's each one contributes 1, so that is fine. And for the boundary contributions, you get 1/2 or 1/2 of n, so 1/2 of n times n is the number of vertices, and each boundary, sort of the edge point, contributes 1/2, so that is indeed the correct term. Yeah, and finally there's this red, what I call the combinatorial junk correction, -1, which survives there. This -1 was in fact minus 2 pi divided by 2 pi. So minus 2 pi as in n minus 2 times pi. That's where it came from, in fact. Okay, so that's Pick's formula established. Okay. If you manage the water, just not by flooding, but in a more judicious fashion, you can also solve algebraic equations with real coefficients. So let's look at an algebraic equation. Again, coefficients are real, but I'm going to look for real roots. And when you are given such a thing, write it in the following fashion, so that on both sides, all the coefficients are positive. So if you have a negative coefficient for a certain term, move that term to the other side. Okay, so that's what it is. Now, here's how you can use water. What is the upward buoyancy we get if we dip these objects into water? For example, let's take this cylinder. This is a solid cylinder. There's no hollowness inside. Okay, and if you dip it to depth x, well, Archimedes says that the buoyancy is proportional to the volume that has been displaced by this thing inside water. So the volume of water displaced. So that is proportional to the depth, because the cross-sectional area is constant here, right? If you had this kind of paraboloidal shape, then it turns out that the volume that you get if you dip it to depth x and truncate it is proportional to x squared, and for cone it is x cubed, and so on. So you get those objects whose buoyancy when submerged to x is proportional to x squared, and x cubed, and so on. That is very good. What about an object that has constant buoyancy? Well, you get something like this. You see, you put a very thin flat disk, if you like, or something like that. As soon as you dip, you get constant buoyancy, because the entire thing is dipped. But if you don't dip, you get zero buoyancy. So that is proportional to 1. So by capturing the various terms of the polynomial by those buoyancies, you can construct the following gadget. You can take, for each term on the left, you can take, for example, if you have something like 3 times x, you take distance 3 from the pivot, and then you put the object that has buoyancy that behaves like x. And if you have, let's say, 1.2 times x squared, you put at the distance 1.2 from the pivot and an object that has x squared behavior, and so on, and on the other side the same, and this pivot is frictionless. And you dip the whole thing into water until those two sides balance, and you have horizontal equilibrium, and that depth is the root of the algebraic equation. Okay. We shall wrap up this brief tour of a hugely rich world of physical applications of mathematics by discussing the Euler characteristic, that is the oldest and probably the most fundamental invariant, topological invariant that we have. Most fundamental in the sense that, according to the splitting principle, if you can control the Euler class, you can then control all characteristic classes of a fiber bundle. Yeah. So Euler characteristic. Let's start with S2, that is the two-dimensional sphere inside a three-dimensional space, if you like, okay? And that's a genus 0 surface. As usual, we want to have vertices and edges and faces, but we shall use the language of an electric circuit. So we shall cover that surface with a circuit of, let's say, copper wires, having beta 0 nodes, beta 1 wires, and beta 2 panels. Wire means those edges, and panel really is a fancy word for each face, okay? And having covered this in any fashion that you like, and you know between parentheses that, of course, all the characteristics are alternating some of these things, and having covered this, take any two nodes and put the voltage across, okay? Put the battery between. This is a rather dangerous task, so I'm going to ask my colleague Chatterjee to do this. As soon as he connects, it goes zap, and suddenly currents flow through all edges, all the wires. We don't know what those currents are because that's a difficult problem to solve. But we can ask, what are the values of the currents in the wires? Well, let's at least set up the problem. Yeah? After all, nature solves the problem instantaneously, right? We may not be so clever, but nature knows immediately what current flows through each wire. So let's set up the problem. How many unknowns are there? Well, we want the current value through each of the wires. So there are beta 2 wires, beta 1, wires, so beta 1 unknowns. What are the constraints which constrain those unknowns and allow us to solve for beta 1s? Well, these constraints come from what are called Kirchhoff laws in electric circuits. The first law says that around each vertex, okay, there are wires coming in, and some wires are carrying in current and some wires are carrying out current, but the net flux into this must be 0. Otherwise, there will be a depletion or accumulation of charge, and that's not an equilibrium station. That's bad. So at each node, current in equals current out, the total current in equals total current, and that's, if you like, a divergence 0 condition at each node. It looks like there are as many such constraints as the number of nodes, that is beta 0. Actually, this is a bit fishy, so I put the question mark there. But moving on, another Kirchhoff law, Kirchhoff number 2, is that around each panel that you see, around each cycle that you see, the net circulation is 0. That is, the clockwise current flowing equals the counterclockwise current. Otherwise, there would be non-equilibrium, there would be a curl present in a harmonic problem, and that is not possible. So curl is 0 condition, is this condition, and there seem to be as many as the number of panels, that is beta 2. Well, I put question marks because it turns out that those counts, beta 0 and beta 2, are overcounts. Why? Let me convince you by arguing as follows. Suppose that you impose the 0 divergence condition at each of the vertices, except the top vertex in this cartoon. Okay, so all the other vertices have the property that the no net current is flowing in and out. Yeah, there's a lot of sort of current going all over the place, but net calculation is 0 at all the other vertices except at the top. Then I claim that the top vertex, it's also 0. Because after all, the current that comes into the top vertex is the net sum of the current that came out of the rest of those vertices, and vice versa. So if the rest of the vertices are law abiding, the top is also law abiding. That is, we overcounted by 1. Yeah. This has to do with the fact that if you remove a little disk from the surface, the rest becomes contractible. And then similarly, for the panels, if you impose this 0 circulation around each cycle, and it turns out that the only remaining cycle that you have satisfies the condition automatically, so beta 2 minus 1. So you have to have beta 0 minus 1, beta 2 minus 1 for independence of those counts. I then copied those counts here. Number of unknowns beta 1, and number of constraints, beta 0 minus 1 and beta 2 minus 1 for S2. Now, the 0th law of the theory of equations, as it were, says that if you are solving any equation, any system of equations, and you want the existence of solution, well, the least you can ask is that the number of unknowns must exceed the number of constraints, yeah? So that it's easy to fit trial solutions to unknowns, and then one of them will work because it's not very heavily constrained. That's the existence. So you want the existence to be easy. On the other hand, in the dually, in the other direction, if you want uniqueness, then the number of unknowns must be less than or equal to the number of constraints. The number of constraints must exceed, because constraints are so severe that you don't allow 2 solutions. Yeah? Maybe you end up having 0 solution, but that's uniqueness too. So you have to constrain it heavily. And at the same time, nature determines the values of those currents instantaneously. In other words, for this problem, we must have existence and uniqueness at the same time, which means that those two sides, number of unknowns must equal to the number of constraints. That is, beta 1 must equal beta 0 minus 1 plus beta 2 minus 1. Okay, and if you rearrange the Euler characteristic of S2, then, which is the alternating sum beta 0 minus beta 1 plus beta 2, is 2, which is exactly right. So we didn't have to do anything. We set up a physical illustration, and nature computed the Euler characteristic for us. What about not S2, but the surface, orientable surface of genus G, which is in general G handles like this? Yeah? Well, that means that you have those extra cycles, 2G extra cycles, each pair of cycles around each of the holes or each of the handles. By the way, another final digression. It's traditional for topologists to draw a torus like this. Everyone likes to visualize a torus like this. I used to be a card-carrying topologist. My card expired some years ago, but at some conference many years ago, I drew a torus on blackboard like this, and everyone got really upset. I don't know why that is. So here's my picture of upsetting picture of genus G surface. And for that, as I said, there are two G nu zero curl constraints. You see, the zero curl constraint around each of these does not come as a consequence of the zero curl constraint on all the panels that I mentioned, yeah, because these are, if you like, independent. So we have to add 2G new constraints because they are not dependent on the old zero curl constraints around the panels. In other words, beta 2, number beta 2 must become beta 2 plus 2G. And here, therefore, beta 1 equals the number of unknowns equals number of constraints argument, beta 0 minus 1. That's the same, but now for the Kirchhoff of 2, you get beta 2 plus 2G minus 1, and rearranging, you get the Euler characteristics 2 minus 2G, and so on. I would like to leave you the pleasure of the exercise of figuring this out for non-orientable surfaces. This is a bit challenging, but very amusing. Okay. You know, I have the impression that here, I'm reinventing the wheel of Hodge theory, because in this traditional Hodge theory, you do cohomology instead of homology, but it's more or less the same thing. And in each cohomology class, you're supposed to be able to choose, by doing elliptic regularity, hard analysis, a harmonic representative. Yeah? And here, of course, there's a harmonic situation. Everything is in equilibrium, and you are putting electricity, which is also, of course, smells of harmonic, and probably it's doing discrete Hodge theory and so on. Okay. It is now time to say goodbye. So as a coda, I should like to tell you about Darwinian theory of gravity. Darwinian theory, you see, a long time ago, about 400 years ago, Newton said, well, an apple falls from a tree because, you know, the Earth and apple attract each other, universal attraction at the distance. And, you know, if you calculate the apple, then follows this Newton's law and falls accordingly. And then 3 centuries later, about 100 years ago, Einstein said, well, you know, another way to look at this, and the more precise way, is in terms of space-time geometry. The presence of mass of the Earth distorts the metric of space-time, and if you calculate the geodesic of the apple in that metric, then it looks like it's falling and so forth. But what does Darwin say? Darwin says apples fall from a tree as a result of natural selection. You see, a long time ago, there were 2 kinds of apples. One kind of apple fell downward, but another species of apple fell upward. But then natural selection took place, and upward falling apples suffered a reproductive disadvantage. So we are now left with only downward falling apples. To my esteemed audience out there on the other side of the screen, and especially to Suraf and Mahan for their very kind invitation for this great honor of giving the TMC Distinguished Lecture, thank you.